Okay, so it's time for us to get started. Hello, ladies and gentlemen, and thank you for joining KEMET's webinar on filtering and power conversion in high voltage green and industrial applications. My name is David Adib, and I am KEMET's Senior Technical Marketing Engineer based here in Florida. We have our presenter today with us, Hector Nieves. I will let Hector introduce himself in further detail. And with that said, I will turn it over to Hector, who will begin our presentation today. Hello, Hector. If you can, please go ahead and introduce yourself to our audience, and you can get started with your presentation. Thank you.
Yes, thank you, David. Hello, my name is Hector Nieves. I'm a product manager for the Film Business Group in KEMET Electronics. I am doing this presentation on behalf of Kalin Georgi, who is our product manager in Bulgaria, in charge of the power canister film technology. So Kalin has some difficulties with the audio and with internet at this moment, so if he's joining us later, so I'll pass the presentation to him. But in the meantime, I'll be the presenter for now. My role as a film product manager in KEMET, I am the marketing product manager for KEMET. I'm basically reporting to the Fort Lauderdale office as David. So let's start. So today we're going to be talking about film solutions for a high power conversion system. So there are two technologies in KEMET that we just couple of weeks ago we released, and we want to chat about that to let you know the advantages of that technology, and then also we'll show you some of the advantages of our new documentation and new tools that we have. So to give me one moment. This is how the webinar is going to be. It's going to be an introduction of film technology first, mostly polypropylene technology and for power film capacitor. And then we'll do some examples of how to calculate light and the process of designing a capacitor with KEMET film technology. And later, we're going to be talking about the two technologies, as I mentioned. One is the AC filter solution, and the other one is the DC-Link technology solution for the power canister technology. And then we'll do some review project examples so you can see how important it is to do those designs and those follow-up design with you as a designer in this kind of project. Okay, let's start. By the way, David, can you hear me well?
Yes, I can hear you perfectly fine.
Okay, fantastic. So let's do a brief kind of introduction about dielectric technology in film. So KEMET is one of the few companies in the world that can handle different dielectric technology. So on the table that you see here, you see polypropylene, polyester PET and PEN, and a special PPS. And summarizing some of the advantages of this technology, you can see on the table that some of the advantages of the polypropylene also I'll discuss later about the plot on the right. So some of the advantages that the polypropylene technology has is can handle a lot of current technologies compared versus the polyester PET, PEN, and PPS, but also has a very stable voltage stability in temperature and also in frequency. So you can see it from the right how the polypropylene technology is just basically fluctuating on a different percentage of capacity between 2% to minus 2% and a very wide range of temperature. So you can see it's one of the most stable dielectric technology. And then also some of the advantages of this technology is also related to the dissipation factor. You can see that the dissipation factor of polypropylene technology overpass, the capability is much less than the other film technologies. That's one of the reasons why we, KEMET, decided to use polypropylene as a capacitor for high power. So because it's very important to manage a lot of current, it's very important to manage no overheating, and also important on the AC kind of situation where a lot of ripple situation or harmonic content is very important. So in this case, there is one limitation of polypropylene that you can see here. So it's not suitable for high temperatures. So it's a technology that it can reach levels 105 Celsius degree. We in KEMET, we develop lately some technology that can reach 125 Celsius degrees for a certain amount of hours. So we're getting closer and closer to develop a technology to 135 Celsius degrees. But at this moment on the power film technology, 85 Celsius degrees, 70 Celsius degree, and 105 degrees, mostly kind of industrial level. And that is one of the advantages of polypropylene. I mean, one of the limitations of polypropylene. However, the advantages are one of the best dissipation factor and one of the best stability in temperature and also in frequency. And that is the reason why we select polypropylene as a power technology for power application. So talking a little bit more about the internal construction, there's different ways to do the metallization for depending on the application. So you can see it on the left, it's a flat technology. It's very kind of how the technology for metallization in capacitor started. We still produce that. I mean, we typically use that flat technology for a standard capacitor, for low power capacitor, and also for capacitors that are EMI suppression capacitor, kind of a standard. Typically it's aluminum. Some of them are using zinc, depending on the AC or the DC voltage. You can see that we use mostly zinc for AC application, or we use this aluminum for DC application. And there is also the heavy edge. And then more and more complex is the wide heavy edge and soft slow. Those two technologies are the ones that we typically use for DC applications, like a DC link capacitor you're gonna see in a couple of minutes. And then we also do heavy edge on AC application, but also we do the soft slow level. Advantages of that, we can customize the level of resistance, we can customize the level of cell healing, we can customize or optimize the level of energy, current passing through the connection of the element. So that's one of the technology that we will use in our technology and our power film capacitors that you will see in a few minutes. So, and then let's do a small summary here. I'm not gonna go through all this material. You have this material available on the KEMET web in a couple of days. So, but this is an overview of how we have technologies for different levels of power, how we have technologies on AC filter application for different kind of construction. So some of the application is the smaller, the radial capacitor to low capacitor, and is related to on the PCB board side. So, but more power capability in level of 100, 300 kilohertz, or I'm sorry, kilowatts, or 1 megawatt level. Now you are considering the situation of designing using canister technology. On the canister technology for AC application, one important factor is we design technology with overpressure safety devices, because we require certain amount impregnated resin or oil inside to protect the capacitor. And then I'll talk about that a little bit more later. But in this case, solid technology, we have the solid technology, we have also the resin oil impregnated technology with safety devices. So of course, typical application for that are inverter, motor drives, and battery chargers, as you are aware. And then some of the advantages of this technology, again, is polypropylene technology, is they're optimized for AC performance. So all this technology basically has zinc metallization and a special profile of metallization, in particular C44PR, that we're going to be discussing later. So industrial market, mostly in this case for the large capacitor, is on the green energy or alternative energy, and also on the industrial level. Those are the most applications that you can see. And again, you'll have this product brief selection in a couple of days in the website. Similar situation for the DC link technology. For the DC link technology, KEMET has different profiles of technology. So starting from the low power R75H, which is a multitasking capacitor that is also a pulse capacitor, as it could be used as a snubber, it could be used as a resonant capacitor. And then later, next, we have the C40Q that is basically 2 or 4 connections there. It's completely automotive industry, driven by the automotive business market and also the industrial. And then passing through the large technology, you're going to be talking about C44UM, which is that's the capacitor that you see here on your right. And then, of course, if you are aware, KEMET also has technology for brick technology, for automotive and also for industrial. We can design capacitors with high capacitance values and high voltage application for dieseling. In this case, the metallization is mostly aluminum. So, and then it could be related to application for dieseling technology and also for DC filtering. So in the output filter also charging station, for example, or it could be also used as an energy storage application level. So let's talk about now a little bit more deep into what is the process that you or we can support you and we can assist you when you are designing a capacitor for your system. So we started, the designer typically knows exactly what the voltage and the capacitance they're looking for, or they start thinking, okay, I need to design a DC-link capacitor or DC-link stage, or I need to design an output filter LCL that with this factor, with this voltage, with the capacitance. So you come to us, and then we decide, okay, let's think about what is needed and what are the applications, and those are what are the parameters that you need to design this capacitor and to be sure that this capacitor will meet your spec, not only on capacitance and voltage, but also in life and reliability. And that is where our FAEs and our product managers start working with you. You can select the capacitor, but even yourself, you can do the calculation yourself. And then one of the main points here is that you need to create a mission profile for a better understanding what is needed. So, and then with that mission profile, with those details, you can now pass and calculate the hotspot temperature. So when calculating the hotspot temperature, you can get also other values there. You can get power losses by the metal, by the dielectric. Voltage current calculation is not rocket science, but it's information that you can do yourself with the data sheet and also with the support of our FAEs and also with the support of our product managers. So that now this situation is calculated, we can pass to the hours and lives and reliability. Again, this is something that you can do some simple calculation with data sheet, and at the same time, we can also support you with more deep analysis in this process. And of course, at the end of the process, you will select the sample, and it's something that you say, okay, the values are correct, is a potential solution, let's test it. So, and then that is the process when you get to the point of selecting the capacitor and getting simulation and doing some testing for your qualification. So let's pass for the first step, mission profile. What is the mission profile? Well, a mission profile, this is an example of kind of basically the typical information that we require to ask you to see what is needed. So of course you have the selection of your capacitor. You need to decide, okay, I need this amount of capacitance. It could be capacitor in parallel, it could be capacitor in series. In this case, typically, film capacitor, they don't need a series connection because they can get to 1500 volts, but in this case, you need higher voltages. Yes, you can do capacitor in series as well as you do with electrolytics. And then some key parameters. I mean, you do your voltage, you do your current harmonic content, and then making sure that they don't pass the limit of the data sheet. And that is very, very important step, okay? So, because if those limits are overpassed, you'll see how they could be compromised as well. And of course, depending on the technology, in this case, this is an example of DC-link capacitor calculation, okay? So once you have that, you also have certain parameters in your design. Okay, my maximum voltage, my normal voltage, and we can create kind of a matrix to do those calculations for different scenarios. But it is very important to have all those details. So, and then of course, the primary harmonic, and then you can also provide other harmonic, which is very, very also important as well for the calculation. It could be very critical for the AC filtering, but at the same time, it could be also critical for the DC link. But for the DC link, there are certain levels of calculation that could be reduced. And then, one little detail that is very important, I know it's very difficult for some designers to have the situation of what is my mission profile, where my technology will be operating, what are the conditions that I'm expecting. Of course, depending on the industry, every condition is different. So, but it's very important to have an idea, what are the worst case scenario, what are the best case scenario, some kind of basically a standard level of percentage, how long this part will be surviving and how long I want this part to survive for how many hours in these conditions. So this is very important information because it helps us to be more precise, and it will help you also to be more precise to determine the life of the capacitor. So, Some examples, again, for example, I put some example here, 55 Celsius degree condition, only 20%, that's the worst case scenario. And 45% is kind of a standard scenario for an application. And airflow, altitude, any details related to the condition of the ambient surrounding the capacitor is very, very important for the calculation of life. So keep in mind that. Now, let's go to calculate the hot spot of the capacitor. So that's the next step. Once the information is collected, all the information, ignition profile, voltage, current, harmonic, life expectancy, feed value. So now what is the hot spot? The hot spot is the point inside of the capacitor that has the higher temperature rated under the condition, on the normal operation condition. So in this case, so you have a capacitor that is overheating internally because there are some RMS passing through, and then the ESR is overheating together, are overheating the capacitor, the dielectric, and also the metal inside of the capacitor, and it creates a hot spot. That hot spot is basically related to the ambient temperature. So reaching the ambient temperature conditions surrounding the capacitor, and then adding the hot spot, it will give us the total heat inside of the capacitor, what we call it the hot spot. So it's the ambient temperature surrounding the capacitor plus the delta T that you see between the ambient and the hot spot condition. This is the total hot spot condition, see here. This is a summarized way to do it. And then we do it because depending on the application, if it's a DC link application, the frequency containing the polypropylene, as you saw before, is very stable. So the frequency between 1 kilohertz, 2 kilohertz, up to even, I would say, almost close to 100 kilohertz, the calculation with the ESR that we provide to you in the data sheet, which is at 10 kilohertz, is kind of stable. So, and I'll show you an example later, okay? You can see how stable it could be. But however, if you are now being more into this situation, you can do every harmonic concept, which is typically mostly used for DC application, but also mostly for AC application because more harmonic. So that one this is calculated, one little information that you will find in the catalog is the thermal resistance. This thermal resistance will translate this situation of power losses to Celsius, to temperature, okay? So that thermal resistance is given by the K size of the capacitor. So, and then of course, the most important thing is that you need to make sure that you don't overpass the temperature hotspot to the maximum temperature that this capacitor is designed for. And that is basically the last equation that you see there, okay? So once you have your calculation of your hotspot, and then now inside, again, we are using the data sheet from the technology, from the DC44UM, for example, in this case. So we can calculate the life of the capacitor. In the case of the C44UN, and we can also calculate the feed value, the reliability performance. So in this case, we'll provide you in the data sheet the life of the capacitor, and also we provide you the feed of the capacitor in certain level of condition. Temperature, different temperature values from 85 to 70, 60, and 50. So if your hotspot is meeting some of those values, you can follow the equation, or you can follow the curve, the plot, and calculate an estimated life of the performance of the capacitor. So in the case of the C44PR, which is our AC filtering, we kind of split the plot. We have the life calculation and the feed plot. So keep in mind that there is another factor here. Is you see the voltage ratio here. It's the voltage that you apply, the VDC voltage applied to the capacitor, divided by the rated voltage of the capacitor. So you can see that the rating film technology is very important, not only in temperature, but also in voltage. It will give you more chance. The closer that you approach to a lower derating factor, better derating factor, the higher possibility that you can reach levels 100,000 hours. So it's very important to keep in mind that not only heat, but also voltage derating applied to the capacitor is also important to related to the life extension of the capacitor, okay? So once this is designed, everything is okay, looks okay, the numbers are close to your range of life expectancy and feed values, then it comes the next step. So what are the next steps? Okay, so let's give me sample. Let's order sample through our distribution channel. But we can also provide you technologies or samples technology with thermocouple. So which is important, that it will help you to calculate. This thermocouple will be close located near to the hot spot of the capacitor, but just in this case. The only chance that you have, other than not having the thermocouple, is connecting the thermocouple outside of the capacitor, which is going to give you a range. Kind of, you need to calculate the range of what is inside of the capacitor versus the surface of the capacitor. Other level of application, we have the capability as well in our R&D group to do thermal analysis, to do ESL analysis, frequency analysis. So if your design require a more deep analysis, what is going on, because you have altitude, you have airflow passing to the capacitor. So we could support you with that analysis as well. And then at the same time, we can also support you with changing or adjusting, I would say not changing, so optimizing the material of the capacitor, demetallization, the resin, the connection, the wire connection. So we have that capability as well at KEMET. So, and then another step is that we can also, once you do your test, we can do also the analysis. After you perform certain amount of tests for your qualification, we can also review the capacitor and see if there's any potential damage. For example, here, there's a capacitor. This is a string case of degradation because of corona effect situation on some of the layer of the capacitor. But we could do this type of analysis as well at the design level. So you have something that you already have the calculation, you already calculated, you already tested your part. Now you want to see internally how the part looks like. So to make sure that it's still under spec for our situation of slide calculation as we did before. So let's do an example here. Just a quick example. What I was speaking right now is, let's talk about a D-link example calculation, okay? So let's assume this is a capacitor that you as a designer require, a 320 microfarad and an 1100 volt, and then to be applied a voltage of 800 volt DC in the line of the capacitor. And this is a DC-link capacitor as well. And then expected reliability is equal or less than 12. And the capacitor life expectancy is at least 100,000 hours. So summarizing, you can do the summarize of the most important ripple current. It could be different ripple current, but in this case, a 40C RMS, and then a frequency of 10 kilohertz. So, and the maximum ambient condition surrounding the capacitor is about 40. So keep in mind, this capacitor could reach to 70 maximum temperature on the hot spot situation condition, okay? So in this case, you go to the data sheet and you go to KEMET website, obtain the data sheet, and then you can see here, there are certain values here. For example, the thermal resistance is here, and you can see also the ESR values that you need as well for the capacitor calculation, okay? So now the next step is the hot spot. Let's calculate the hot spot in this particular capacitor. So of course, you have the ambient temperature, which is of course 40 Celsius degree, and you now calculate the hot spot based on your ESR and the RMS current that you have. So okay, it's a simple calculation, 29.5, almost 30 Celsius degree hot spot raise. So in this case, you calculate that and you add it to the 40 Celsius degree, you have a hot spot temperature of almost 70 Celsius degree, which is on the range of this capacitor. So in this case, you can see here is acceptable. Now, in this case, we are assuming an ESR and 10 kilohertz. Sounds like, okay, sounds easy. So 69.5, and then let's assume for the moment that this capacitor has a 60 kilohertz frequency harmonic. So yes, it will be affecting this value. It will be affecting at the end these values of fly as well. However, keep in mind that in this case, an example of this capacitor is just ranging from 10 kilohertz to 100 kilohertz. The main difference is about 2 degrees, or I would say, I'm sorry, 2,000 hours difference. So you're still able to do very good calculation with just assuming a simple equation like this, okay? So now this situation is also, of course, you want to go more in deep, we can do more calculation more specifically. So you can go to select, okay, I want to calculate the ESR of my capacitor at 50 kilohertz. You can do that by using the equation. Of course, the standard equation of tangent delta O, which is the internal dissipation factor of the polypropylene capacitor, plus the effect of the frequency and the capacitance of this. So, for example, if you have 10 kilohertz that is on the data sheet, you can do the RS and find the RS value for 10 kilohertz with the 10 kilohertz ESR and the 10 kilohertz here, and then you know the RS for 10 kilohertz. RS is the losses of the metal inside of the capacitor. So it's considered very stable in frequency in this condition. So now you have in your RS standard constant. Now you can just plot the frequency and you can do now the ESR for different levels of frequency in your system. Again, it's not rocket science, but it's something that will give you the approximation better of the ESR depending on the frequency. So life and reliability, what is next? Okay, we already know that this is a hotspot. And then now we go to the plot and then we select, okay, let's select the 70 Celsius degree plot, which is this dot line coming here. And then the voltage rating that it was calculated, it was a voltage rating of 0.72. So now you just stop in the x-axis here and you go to the 70 Celsius degree hotspot curve, and you can see that this capacitor is almost 200,000 hours life. So the voltage rating plus the hotspot situation calculation, it gives you a life of almost 200,000 hours. So in the same situation with the feed, you go to the 70 Celsius degree plot, you stop here in this dot line, and again, same voltage rating situation, 0.72, and you can see that it's almost close to 10. So that means you are meeting the spec of less than 12 feet, and you are meeting the spec the higher than 100,000 hours. This is a simple calculation that can be done directly with just the data sheet of the capacitor that you see here, okay? Now, let's assume something more complex. Let's assume that you have 3 different mission profiles. For example, a mission profile that covers 20%, 40%, and 40% of the time under certain conditions. In this case, let's assume a C44PR, which is an AC field. And let's assume that you have different current capabilities and different frequencies for that mission profile. One mission profile, or one condition, second condition, third condition, and 4 different harmonics. So, and you also have the different temperature conditions. So yes, making the string condition for that. So yes, it will require to do this process manually, and it's very tedious situation because it has to do every frequency, every calculation at a time at the end to do the final live calculation. But here at KEMET, we have a tool that the FAEs will have in a couple of days, and then the product managers, that we can help you to do those calculations. So, and the idea is just to translate this tool in the future, coming soon, for your access directly to do the calculation yourself. So for all the power film capacitors that KEMET provides. So this is a calculation that is right now, for now it's internal, but we can support you with that. And then what can you collect here in this calculation? You can collect, once you calculate, you have this input from your mission profile plus the input that you require for your electrical performance in the capacitor. We can calculate how is the ripple created by each of those frequencies. How is the losses created by each frequency on that? You can also see the spectrum of losses and ripple situation, which one is your harmonic that is affecting you, affecting your design in more concern. And then at the end of the day, we can calculate the delta T for each of those conditions. And you can calculate the life for even just one mission profile or one condition. For example, this one is 10 Celsius degree, it's going to be 20%, but if it's running 100% of this condition, you can see the life calculated by every of that. And again, it's not rocket science, but it's something that is very simple, just entering the input and entering the information. At the end of the day, you just basically get the life that you're expecting. And you can also get the feed value that you're expecting as well. We're working on that to provide you that as well. But now you are saving all this process to do this process, basically just with your entering the input. Again, this is available for internal right now, but in the future will be translated to a more applicable for casing, our casing platform, okay? So don't hesitate to contact us for more details. Okay, now that you know how simple it is to calculate the life of a capacitor using just simple equation and data sheet and information from the KEMET film technology. So let's go a little bit more into details of what are the technologies, what are these technologies? C44UN is a DC-link capacitor. We have C44 in the past. C44UN is an extension of that technology, C44U, that we have for many years. So some of the changes, some of the advantages now that we have is that are related to the level of capacitance. So we are increasing the level of capacitance to 1800, I'm sorry, to 2100 microfarad. And we also 1800 VDC. And we do that by optimizing dielectric, film material, and metallization. And then now that these technologies being more and more required to be UL kind of certified, is a UL 810 for the construction. The material, all the materials used in these technologies are basically following the UL specification. The life expectancy now, before in the past, maybe you don't remember, we had this technology just ready to maximum 100,000 hours. Now we are able to reach even life situations 200,000 hours. It's just something that you require 300,000 hours. Please contact us because yes, some of these technologies can reach those levels, but we just need to do some more specific calculation for you. Another important step is that we are also increasing the diameter of the technology. So now it's just, we have the 160 millimeter. We're gonna have very soon the 132 millimeters, which is larger. So to levels of high capacitance and electrolytic capacitor with the advantages of a film technology as well. And then some other advantages that we now produce this technology in our Bulgaria facility. Before we only had the facility in Italy. So now Bulgaria is completely vertically integrated for this technology. So we do our own metallization. We don't do the film, we just metallize the film, but that is give us an advantage of optimizing the technology as needed. So just keep in mind that of course the level of quality is much better from the levels of follow-up or tracking for the technology and situation. And of course, price competitive. We are competing with all the big companies around the world, and in our price, very competitive in this condition. So typical application, I'm not gonna go through that because you are more expert than me on that, but if you have energy storage situation right now, I'll show you some example. Solar energy, I'll show you one example. Wind energy, we have those technology as well, and industrial drive. So this is information you can find on our website, and then you will be happy to review with you as needed. So construction-wise is, as I mentioned before, is UL constructed, and then the terminals, everything is following the spec from UL, and the construction inside. So to give you an idea how we can play with the design of this technology, so just a brief idea. So in the left side, you have a capacitor which has a 2.5 million, for example. It's a capacitor with two internal elements connected in parallel. But if by any reason, this capacitor requires, for example, to have a more current capability, more than capacitance, or something that is the perfect design, but at the same time, it could be optimized. So in this level, we just, for example, make an example of a design that we did. Is okay, we have the same connector side, and then instead of having two elements, we put three elements. So three elements capacitor in parallel in this case. So the capacitance in this condition, we just drop it to 1.2 million. So yes, if the capacitance could be compromised, but at the same time, it's following another step that is to manage more current capability in this case. Okay, so that's a typical example that we do design in our factory. We have the capability to do. So another design capability that we have is also since we do the metallization of this technology, we can play with the metallization in this technology. We started with a zinc surrounding the polypropylene dielectric film, and then we added the aluminum, and then we followed mostly this kind of how we call it, hard edge condition. And one of the advantages of this hard edge condition, this is the element on one side. The other element will be something here to the next side to do the complete loop. So this element here, this is strong or wider level of metal, allows to manage more current capability in this technology. But at the same time, the soft flat condition here allows to have a better cell healing capability. So yes, we also play with the resistance of the metallization as well, depending on what we need. We need more cell healing or we need more current capabilities. So yes, that's something that we also have as well, the capability to play with that because we are vertically integrated. So let's pass to the filter capacitor technology, okay? So in this case, the filter technology is people will think, okay, it's a capacitor, it's a polypropylene, it could be used on DC and AC. Yes and no, okay? This capacitor require, in particular, this capacitor require a DC bias. So you need to have, yeah, it has the capability to manage ripple. It has the capability to manage voltage fluctuation, but this capacitor is designed based on, it has required to have a DC bias. So there is not gonna be fluctuation between minus or negative voltage fluctuation. You have to require a DC bias. It's a DC link, despite that, again, polypropylene could be used in AC and DC. The construction internal of the capacitor only allow him to manage certain level of ripple fluctuation, not to the negative side of the loop. As you can see here, it's a DC bias here on the top of this image here that you see on the corner on the left. So now passing to the other capacitor, you can see that this capacitor is mostly designed for pure AC application, high ripple application. It's a construction that is internally, and one of the big difference is that this is an impregnated technology, okay? And I'll talk about that in a few minutes. It has an overpressure safety device because if something happens internally to the capacitor, an overheating, this capacitor could go and disconnect by itself. And then life expectancy in this capacitor, because it's a pure AC technology, ESR is more involved, it's getting more overheating situation, and the transformation of positive and negative situation on the voltage and the current. So yes, this capacitor life expectancy is around 100,000 hours. In the past, C44P that we have in the past was only able to do 30,000 hours, but we were able now to do levels of 100,000 hours and more. And some of the advantages, again, produced in Bulgaria as well. It's our same factory that we produce our dieseling technology, and then it's a UL 810 certified, and it has a very, very strong ripple capability. So one of the other series that we just released the 480 voltages in this capacitor, which is very important for the technology here in America and Canada, where the 480 volts delta connection could be a possibility. So similar applications as the dieseling, mostly industrial and mostly on the inverter aspect as an LCL filter. And that is where some of the advantages that we have with the C44PR now from KEMET. So let's talk about some features of this technology, okay? So people get more familiar with it. So of course, it's a soft resin impregnation. It has some advantages, very good advantages. One, it helps to reduce discharge, corona discharge, and extend the life of the capacitor. How it can do that? So imagine, for example, you have a capacitor, an AC filter capacitor that is solid resin, and then this capacitor is starting to overheat. What is going to happen is that the material, the polypropylene material, starts just shrinking, and then it starts just basically releasing those air and then surrounding the material of the winding of the element. So, but in some point, when this capacitor is passing again to the normal stability of less temperature, so it starts absorbing again that air back when it's the capacitor, the polypropylene starts to expand again to its normal condition. So it starts absorbing, surrounding the capacitor air. So that air surrounding the capacitor is what we call can create corona, and it is air with humidity. So more problematic the situation is that you saw before some of the slides for the failure analysis. So it could start degrading the metal, the zinc metal of the metallization. In this case, the resin is doing that. It's not allowing the capacitor to absorb air close to the metallization of the capacitor, of the element. So instead of absorbing air or humidity, it will keep the resin together there and less chance of corona. Another advantage that you'll see for the soft resin or liquid resin is that it has a better performance on releasing the heat of that capacitor when it's overheating on ripple or high harmonic content situation. So that is one of the advantages of the technology based on that. Now, the other advantage of our technology versus other technologies is that we use metal deck. So in this case, metal deck is a very strong design, completely sealed, versus plastic deck. Plastic deck has some of the disadvantages that it could absorb humidity. The humidity could go into the plastic. Believe it or not, it will go through the plastic. And we have done some testing in the past, and yes, we noticed that situation. So in the case of metal deck, now you are competing with a technology that is better than plastic, but the price as well is even almost close to the level of plastic technology as well. So that is one of the advantages of this capacitor hermetical seal. And of course, the disconnection device. So there are different ways to do a disconnection device. Some of the designers, we have also that technology, disconnect the device from the deck. So the deck will do the disconnection. In this case, the canister is the one who's going to be started making the disconnection. When this capacitor starts overheating, the resin starts expanding, and you can see this notch here on the surface of the canister. It starts expanding inside because there is an over canister inside of the capacitor, and then start expanding and it will disconnect a cable inside, disconnect the cable, the connection of the cable inside of the capacitor. So that will allow the capacitor to avoid potential explosion. And that's the idea. It is something, for example, like AC filtering bank that you have like a 40 of this capacitor, 30 of this capacitor, one capacitor explodes, could be a chain reaction on that. You are basically having a potential very critical damage of a complete unit, even a complete or even hurting someone. So in this case, the idea is just having this disconnection device is to avoid that potential damage as well, okay? There's some limitation here. The hot spot of this capacitor can just reach certain level of temperature. If you require something higher than 80 Celsius degree or 75 Celsius degree, yeah, it might be possible this capacitor might not be the solution. But again, contact us is depending on if we have airflow, you have airflow expansion or anything helping the capacitor. We're also working right now to extend this temperature on this capacitor. In a couple of months, we're going to be releasing a better technology with higher temperature and also with more humidity protection as well, okay? But again, this is some of the good features of this technology. So let's go back now to examples of this technology where being used. I mean, these are just the tip of the iceberg of what we can offer to you. So in the case of solar system like inverter string situation, we have the design of the C44UM, for example, in some of those solar inverters as well. So in the tables, this is a kind of unique technology. This is more like a smart valve for providing reactive power. It could be positive and negative reactive power. I would call it a disruptive technology. So using semiconductor technology instead of using big bang of capacitors, AC filter capacitor that typically the power line has in the past or they still use. Instead of using that, this technology on semiconductor technology to transform positive and negative reactant energy through the line to optimize the line at that moment immediately. So, and then the technology is being managed by our capacitor bank of C44UM, as you can see. And this is another, again, storage energy inverter situation, capacitor internal there that it could be bi-directional. It could be one way or another. It could charge the battery, or it could just use the battery energy to produce power factor correction at the same time to produce energy to the grid. So yeah, technologies of level of 100 of kVA to a level of megawatts situation. That is where you see mostly this technology from KEMET. In the case of C44PR AC filter solution, for example, we have projects that, I forgot to mention, so I mean, this is a good point. So one detail of one of the advantages of C44PR is that because it's hermetical seal, you can do it in horizontal or vertical connection with no problem. So other technologies, it might have some compromise, situation is they are designed in a horizontal way. So that is one of another advantages of the hermetical seal metal deck of the C44PR. So we have projects right now running for HVAC applications in this case, for the pumps in the case. We see projects for AC electric traction system, for high power systems on this technology as well. And of course, UPS, still stored energy, more and more, everything is going to data and communication. So this technology could also be applicable in this case for the UPS business as well. Again, level of kVA or 2 digits, 3 digits to the level of megawatt digit as well for the technology, okay? So those are some of the technology that we wanted to show you today about KEMET film power film canister. So that will conclude my presentation today. And then if you have any questions, thank you very much for your time.
All right, thank you, Hector. We actually do have a question from our audience. And the question says, in the specification, there are two attributes, temperature range and rated temperature. Which defines the maximum hotspot temperature?
The hotspot temperature will be the range temperature. I mean, again, it's maybe Calling with our expert in the technology. If he's connected, maybe he can help us to answer. But the idea is you have to meet the ISC expected temperature range, right? You have the minimum temperature, the maximum temperature, and the level of I would say, storage humidity. But in this case, the maximum temperature that you see there is the what we call the maximum not rated temperature. I would say is how do you call it in the cattle? Let me just give me 1 second. We call it just to make sure that I'm not answering the wrong question. We call it upper temperature. That's what we call it, upper temperature range situation. Yes, in the case of this capacitor, for example, C44PR, if you overpass situation of 75 Celsius degree, the possibility of disconnecting this, it could reach 80 Celsius degree, but it's the possibility that this disconnection will expand. But yes, it's kind of confusing the situation. You need to use what we call the upper temperature situation that we have in the data sheet.
Okay. And the second question we have says, do you have any KEMET capacitors for VSC HVDC power conversion application in the field?
Yes, we do. Again, my apologies if I don't have my expertise in this was mostly America, but my associate from Europe might probably jump into this. We have technologies like C40FT and C44PR on VFD, variable frequency drive. Yes, we designed this technology in variable frequency drive. In my case, as my product manager experience, I was able to design this technology on VFD, depending on the power, depending on what you are doing to the PCB board side. But this is also a design that could be used in VFD, variable frequency drive as well. Okay, but depending on the power. Sorry for that. Let me go back. Depending on the power that you are managing, depending on your design, if you want to go to a solid resin technology with this capacitor in series parallel, you can do delta, you can do Y on the VFD, but you can do, depending on how much power you are managing, you just jump to C44PR.
Okay. And the third question we have says, please remind us again which applications would require zinc metallization and which is best for aluminum.
Okay, zinc metallization is mostly used on the AC filtering application and on all our, what we call a safety capacitor, EMI suppression capacitor. And it can be, is a better solution for when you see pure AC signals like this, passing from positive, not pure, I would say with ripple or harmonic, but the capability that's going from positive to negative, we design basically with zinc. On the level of this link, we do design mostly on the level of aluminum. So But keep in mind, I mean, there is a little detail here. Okay, it's a technical detail. All the technology, DC-link and AC filtering, they require certain layer of zinc to connect first to the polypropylene dielectric. And then we can add more zinc or we can add more aluminum next to the zinc. But there's always going to be a little bit of layer between the zinc and aluminum in this case, because we need to have a very good connection between the plastic and the metal. So, and connecting aluminum directly to the polypropylene is not the best option. So yes, but typically on the top is mostly pure aluminum, and then this one is, and the other one is mostly zinc technology as well.
Okay. And the last question we have here says, what is the impact of the humidity on the lifetime and the reliability of this technology of capacitors? Do you take it into account in the lifetime estimation?
That's a good question. At this moment, let me go through this calculation here. You can see that we talk about relative humidity, right? So this capacitor has certain levels of relative humidity capability. Yes, we have technology that are more designed for what we call harsh environment capability. So at this moment, we will be releasing coming soon, as I mentioned before, next level of this technology, this link canister and an AC filtering canister power film with more capability of humidity. How is affecting the life? Yes, if by any chance you have a design that require a level of, let me go back to my calculator here. If you want to design a capacitor that require harsh environment condition, we need to let you know as a designer, okay, this is what is considered harsh environment based on the temperature, based on the relative humidity. So that information is not there yet. If you are working right now with a design that it has the potential of being a harsh environment, contact us and we'll do the calculation for you, because it requires a certain level of extra calculation in this at this moment. But in the future, coming soon, yes, this calculator will be also related to harsh environments, similar to what we have for other series that are really harsh environment. But at this moment, the degradation will be potentially damaged. Yes, it will be some degradation, as you can see here. Let me go back again, guys. Sorry for passing through this. But the biggest problem, the biggest concern that we have is the degradation of the capacitor like this, what you can see on the right. So yeah, it could be the metallization could be degraded. And that is where we need, to help you to design or to review, is that a level of harsh environment is affecting this technology. Again, we have technology to prevent this, but not right now in the canister technology right now, but coming soon.
Okay, well, these are all the questions that we have received, and we're actually approaching the end of our allowed time here. So thank you, Hector, very much for this informative presentation today. Thank you, ladies and gentlemen, for joining us today. I wish you all a pleasant day and hope to see you soon again. Have a nice day and goodbye.
Thank you so much. Thank you, David.
Thank you. Bye-bye.
Thank you, everybody.